Welcome to the ninth lecture of the MOOC on parallel algorithms. In the previous lectures, we have seen several algorithm design techniques. We will continue with the discussion on algorithm design techniques. Today, we shall see an algorithm design technique called symmetry breaking. For example, when we have several entities conflicting with each other for some resource, you can construct a resource graph, a conflict graph for those entities. And then when we allocate the resource, we might want to allocate the resource to entities that do not conflict with each other. So, we have to break the symmetry between the entities in some way. So, this is the essential idea of a symmetry breaking. We shall study symmetry breaking in the context of a linked list today. So, we have seen linked lists before in this course, and we have done an algorithm for ranking the linked list. So, let us say we are given a linked list in an array. You are familiar with the physical representation of a linked list. In the physical representation, the nodes are jumbled together and are given in an arbitrary order. That is, the order in which it is given in the array has no relation to its logical order. For example, if this is the first node, you indicate the first node using a head pointer. This node points to another using the next pointer, which will point to another using the next pointer, and so on. So, we have seen how the list can be ranked when it is given in this form, but the problem that we are going to address is different. We are given a linked list in the physical form, and what is needed is to vertex color the linked list. This is a special case of the vertex coloring of graphs. When we are given a graph G equal to VE, where V is the vertex set and E is the edge set, we say that a coloring of G, a vertex coloring of G, assigns a color could be just an integer, to each vertex so that no two adjacent vertices get the same color. So, the problem is just this: every vertex of the graph must be assigned a color, and no two adjacent vertices should get the same color. It is possible to repeat the colors. The number of colors used could be much less than the number of vertices in the graph. So, this is the graph vertex coloring problem. We say vertex coloring in particular because we could also talk about the edge coloring problem, where we assign colors to the edges of the graph. But in this lecture, we are going to consider the problem of vertex coloring, and that too for a linked list. So, let us consider a logical diagram of a linked list. So, as you can see, a linked list is a bipartite graph. You can classify the vertices into two sets so that every edge is from one set to the other. So, that is the definition of a bipartite graph. So, a linked list is a bipartite graph, and therefore, it can be two colored. That is, you can use at most two colors to color the linked list. So, there are two distinct colors to this linked list. One is this. You can give a color of 0 to the first vertex, 1 to the second vertex, 0 to the third vertex, 1 to the fourth vertex, and so on. So, every odd vertex gets a color of 0 and every even vertex gets a color of 1. This is one possible coloring. The other possible coloring is to give a color of 1 to the first vertex, 0 to the second vertex, 1 to the third vertex, 0 to the fourth vertex, 1 to the fifth vertex and 0 to the sixth vertex. So, in this case every odd vertex gets a color of 1 and every even vertex gets a color of 0. So, there are two colorings for the linked list. So, these are what are called the two vertex colorings. We call it a two vertex coloring because we are using two colors. Now, a two vertex coloring of a linked list can be done using the list ranking algorithm. We have already seen a list ranking algorithm which runs in order of log n time using n processors on an ER-EWP RAM. We can use the same algorithm here, and after finding the ranks of the vertices, I can take the least significant bit of the ranks. So, for this list, if you rank the list from the left end, you will be giving ranks 0, 1, 2, 3, 4 and 5. So, if you take the least significant bit, you will get 0, 1, 0, 1, 0, 1, which is the first coloring. A bit flip of this will give us the second coloring. So, a two vertex coloring of a linked list can be achieved using a list ranking algorithm, and this can be done in order of log n time using n processors on an ER-EWP RAM. But today we are going to see a much faster algorithm. I shall show that the vertex coloring of linked list can be achieved in order of log star n time, where log star is an extremely slow growing function, provided we allow one more color. That is, instead of two vertex coloring, we will be three vertex coloring. First, let me define this function that is called log star of n. For an integer n, log star of n is defined as the smallest I, so that when logarithm is taken I times over n, we get a value less than or equal to 2. Log star of n, where n is an integer, is the smallest I, so that when log is taken I times on n, we get a value less than or equal to 2. For example, let us consider the number 2 power 65536. If you take logarithm of this number once, you get 65536. You take logarithm once again, you get 16. You take one more logarithm, you get 4. You take another logarithm, you get 2. So, when you take logarithm 1, 2, 3 and 4 times over 2 power 65536, we get a value of 2. Therefore, log star of 2 power 65536 is 4. Even for a number as large as 2 power 65536, log star is only 4. And how big is 2 power 65536? This is 2 power 16, which is far greater than 10 power 80. and 10 power 80 is approximately the number of atoms in the universe. So, the number that we are talking about 2 power 65536 is extremely large indeed. So, even for numbers which are extremely large, so large that we are unlikely to encounter them in real life, even for such numbers the log star value is at most 4. Therefore, for all numbers that we encounter in reality, log star is less than or equal to 4, which shows that log star is a very slow growing function indeed. So slow growing that it is practically a constant. So, we are going to show an algorithm that runs in order of log star n time using n processors on the ER-EWP RAM. The only thing is that for this we have to pay a price in colors. Instead of 2 coloring, now I will be using a 3 coloring. So, now let us see how the algorithm proceeds. We begin with an initial coloring. In the initial coloring, we give every vertex a unique color. The purpose is to give every vertex a unique color. We can give every vertex a unique color if every vertex is colored with its index. So, the color is the same as the physical index. That is, in the physical representation, we have all the nodes given in an array. These nodes are numbered from the left end in this fashion. They are numbered consecutively. So, they are all going to get a unique number. Of course, we will start the coloring from 0. So, if we have 6 nodes, we will be coloring in this fashion. So, in general, if we have n nodes, the colors will range from 0 to n minus 1. So, the number of bits required to represent these colors would be ceiling of log n. The initial colors can be represented using ceiling of log n bits. So, these are the initial colors. Every vertex has got a unique coloring. Therefore, we can say that the coloring is valid. That is, 2 adjacent vertices will not have the same color. Now, the algorithm proceeds in a number of iterations. So, let me specify an iteration now. So, in an iteration what we do is this. For each vertex in the list, we do in parallel the following. For vertex S, suppose S of x is the successor of x and S of x is the successor's successor. And let us assume that C is the present color function. That is, C of x is the present color of x and C of S of x is the present color of the successor of x. So, with these assumptions, what we do is this: let I be the least significant bit at which x and S of x differ. Then the new color C of x is defined as I concatenated with, that is a binary representation of I concatenated with Ci of x, which is the ith bit of the present color of x. So, we take the binary representation of I, where I is the least significant bit at which C of x and C of S of x differ. We look at the color of x and the color of the successor of x. We consider the least significant bit at which the color of x and the color of the successor of x differ, and then form the new color in this fashion. Take the binary representation of I and then take the ith bit of C of x and concatenate that with the binary representation of I. This is how we form the new color. This we do for every vertex in parallel, and then we keep doing this again and again. This is what one iteration is. We continue with the iteration until the coloring converges. So, let us see how many iterations we will have to execute. First, let us take an example. So, let us say these are the two colors. This is the color of x and this is the color of the successor of x. So, in this case we find that the least significant bit at which they differ is this. So, if we number the bit positions starting from 0 in this fashion, we find that they are differing at the 5th position. The binary representation for 5 is 101. When that is concatenated with the bit value of C of x at position 5, which in this case happens to be 0, this is what is to be the new color for x. So, without the commas and the angular brackets, it would read like this. So, 1010 is going to be the new color of vertex x. So, as you can see, this method shrinks the size of the color substantially. So, this is what we are going to do in the algorithm. In an iteration, every vertex participates. We do this in parallel for every single vertex. What each vertex does is this: it takes its own color and its successor's color. So, every vertex should know its own color and its successor's color. Then it finds the least significant bit at which these two colors differ. Suppose this happens at position I. We take the binary representation of I and then the bit of C of x at that position. When these two are concatenated, we get the new color for vertex x. At the same time, the successor of x is also redefining its color. It would be looking at S of x and itself, it takes those two colors, that is C of S of x and C of S of x, and then it finds the least significant bit at which those two differ. That concatenated by the bit at that position of C of S of x will form the new color of S of x. So, in this fashion, every vertex redefines its color. When this iteration is repeated several times, we would be reducing the number of colors used in the list substantially. Remember, we had begun with an initial coloring of sealing login bits, that is, we had n minus n colors used. Every vertex has a unique coloring to begin with. So, in the initial coloring we had n colors. As this process proceeds, the number of colors will substantially reduce. So, we shall see by how far we will achieve this reduction, and let us also see how this reduction could be achieved. So, first let us show that after every iteration the coloring remains valid. After each iteration, if it was valid before the iteration. We want to claim that the coloring remains valid after each iteration if it was valid before the iteration. So, to claim this, let us consider three vertices x, s of x, and s of x. And C is the present color, the present color function, which means C of x is the present color of x. So, let us say x and s of x differ in the ith bit, that is, I is the least significant bit at which the colors of x and s of x differ. That is, C of x and C of s of x differ at the ith least significant position, and they agree on all lesser significant positions. And let us say J is the LSB at which C of s of x and C of s of x differ. Sorry, in the previous line I used S twice, I should have used it only once. So, here let me change like this. So, vertex x is coloring itself with the binary representation of I, where I is the least significant bit at which C of x and C of s of x differ, and then it also uses the bit of C of x at that position, whereas s of x is coloring itself with the least significant j at which C of s of x and C of s of x differ, and it concatenates that j with its own bit at that position. Now, what I want to claim is that x and s of x are going to get different colors, that is, C of x and C of s of x are different. So, how do I claim this? Suppose I is not equal to j, that is, C of x and C of s of x are differ only at the ith position. All lesser significant positions are the same for them, and C of s of x and C of s of x differ in the jth position, and all lesser significant positions are the same for them, and let us say I and j are not the same. Therefore, any ordered pair of this form is not the same as any ordered pair of this form, because they differ in the first component. Therefore, the new colors of x and s of x would certainly be different. But if I is equal to j, then the two ordered pairs are starting with the same first component, but I claim that they would still be different. That is because x is going to use its own bit at the ith position. So, here it would be using Ci of x to form its new color. So, the new color of x would be I Ci of x, whereas the new color of S of x would be I concatenated with Ci of S of x. Sorry, Ci of S of x. So, what it means is that the new colors of C of x, the new colors of x and S of x are still different even after the iteration, which means the iteration would keep the coloring valid. Provided that the previous coloring was valid. So, the first coloring that we started with, in which we gave a unique color to every vertex, was a valid one. Therefore, the coloring that we obtain after every iteration will be valid. Therefore, we are finding valid colorings through the algorithm. Now, there are a couple of loose ends to be tied. One is the last vertex, the logically last vertex in the list. This vertex does not have a successor, but then in the algorithm every vertex is supposed to look at the successor and take the least significant bit at which its color and the successor's color differ. Since this vertex does not have a successor, where would it look? Therefore, we should provide it with a successor. So, for the purpose of coloring, we would assume that the first vertex is its successor. So, we would make the last vertex point to the first vertex, thereby making the list a circular one, but this is only for the purpose of finding the coloring. After finding the coloring for the other vertices of the list, we can again remove this link. So, for the purpose of coloring, we would make the last vertex point to the first vertex. Now, the question is, how do we find all this? That is, in each iteration we are supposed to find for each vertex the least significant bit at which two colors differ. So, how do we find the least significant bit at which two colors differ? So, let us say A and B are two colors. Let us say we want to find the least significant bit at which A and B differ. We want to find this in order of one time, so that each iteration of our algorithm will run in order of one time. So, what we do is this. Let me explain this through an example. Let me take two integers A and B. So, let us say these are the two integers A and B. Let me take the bitwise exclusive OR of A and B. If I take the bitwise exclusive OR of A and B, I will get a 0 here, 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 and here I will get a 1. So, the first one from the right end is at the position that we want. So, if you count from the right end 0, 1, 2, 3, 4, at the fourth position the two integers differ, and the one that appears, the first one from the right end appears at position 4. So, we have to extract 4 out of this number. So, let us see how to do this. Let this integer be called C. Now, let me subtract 1 from C, which I call D. So, C minus 1 is what I call D. So, if I take C minus 1, what I get is this. position 4 has a 1 in C and every lesser significant bit is 0. Therefore, when I subtract 1 from C, these lesser significant positions will all flip to 1 and position will flip to 0 and the remaining positions will remain what they were. Now, let me take the exclusive OR of C and D. I will get a 0 at all these positions, but I will get a 1 at all these positions. So, we find that there are 5 ones in the result. In the binary representation of C exclusive OR D, we have 5 ones at the least significant bit positions and every other position is a 0. This is nothing but the unary representation of number 4. In unary representation, we represent 0 using 1, 1 using 1 1, 2 using 1 1 1, 3 using 1 1 1 1, 4 using 1 1 1 1 1. In general, we will represent n using n plus 1 consecutive ones. So, you find that the unary representation of a number is much larger than its binary representation. Now, what we have done here is to find the unary representation of the number that we want. That is to find the least significant bit at which two colors differ. We should take the bitwise exclusive OR of them and then subtract 1 from the bitwise exclusive OR and then take the exclusive OR of the numbers C and D, and what we get would be the unary representation of the number that we want. Now, we should convert the unary representation into the binary representation. That is, if you consider the binary representations here, the binary representation of 0 is 1, of 1 is 1, and of 2 is 1 0, here it is 1 1, here it is 1 0 0, and so on. So, what we need is a conversion from the unary representation to the binary representation. We will do this using what is called a table lookup. Since we are dealing with colors in the range 0 to n minus 1, we require log n bit positions. Each bit position can be represented using log n bits. So, there are log n positions at the most. So, we might want to convert numbers in the range 0 to log n from unary to binary. So, let us say for this purpose we construct a dictionary. So, in the dictionary what we do is this: we will form the unary representations and the corresponding binary representations and store them at the appropriate positions. So, at what positions will we store them is the question. Now, 1 is the binary representation of 1, 1 1 is the binary representation of 3, 1 1 1 is the binary representation of 7, and so on. So, we can take an array in which we store these positions, store this dictionary. In the first position, I will store the mapping from 1 to 0. In the third position, I will store the mapping from 1 1 to 1. In the seventh position, I will store the mapping from 1 1 to 1 0, and so on. Now, once I have stored the values in this fashion, I can treat this array as an associative array. So, the dictionary is stored in an array of size n, but even though we have taken an array of size n, we would be using only some locations of the array. we would be using in particular login locations of the array. And once the array has been formed, we can keep reusing this however many times that we want. Yeah. So once a dictionary is formed, we can keep reusing it as many times as we want. And using the dictionary once requires only order one time, as we have seen here. For example, if you want to find the binary representation of 1111, all we need to do is to look at position 15 of the array, where the value 11 will be stored. 11 is the binary representation of the unary number 1111, which stands for 3. So the dictionary can be used in order of one time once it is formed. Therefore, we do not consider the cost of forming the dictionary here, because that's a one time operation, and once it is formed, we can keep reusing it as many times as we want for every execution of our algorithm. So we rely on the fact that this dictionary is available and the dictionary can be looked up in order one time. Therefore, we now find the iteration that we specified earlier can be executed in order one time for every vertex. So for every vertex in parallel, we can compare the colors C of x and C of S of x and extract the least significant bit at which these two differ. Now the next step is to find the bit position of C of x at this position. So we know that I can be found in order one time. What is remaining is to find the bit of C of x at position I. For this purpose, we can form what are called masks. For each bit position, let us say we have a mask. In particular, for the third position, I have a mask like this. So this is corresponding to the third position. So for each position, I will keep a mask. I will prepare a mask in advance. So that is done offline again, like a dictionary, and these masks again could be kept in a dictionary. So to extract the third number, the third bit of a binary number, for example this, what we do is to take the bitwise AND of this with the mask, which will give us and then if the numerical value of the result is 0, then the bit at that position is 0. If the numerical value is not 0, then the bit at that position is 1. So that is how we check what the bit position at a particular position of an integer, what the bit at a particular position of an integer is. So combining all this, we can execute an iteration in order of one time. And we have used only an ER-EWP because there is never any concurrent read anywhere. Vertices need to look at their successors, but then every vertex will first access its own color, then they will access their successor's color. So when x is accessing the color of S of x is accessing the color of S of x. So again there is no read conflict. So the iterations can be executed on ER-EWP. Now let us see how many times the iterations have to be executed. The initial colors had a length of L1 equals ceiling of log n. That is, the colors range from 0 to n minus 1. Each color could be represented using ceiling log n bits. Therefore, the initial colors had a length of ceiling log n. And then the second set of colors were formed by taking these bit positions, the binary representations of these bit positions, and concatenating them with one bit. Therefore, we needed to represent the positions 0 to ceiling log n minus 1. This range we had to represent in binary. That would require ceiling of log n bit positions. So the new colors, the second set of colors, required these many bits plus 1 because we are concatenating them with one extra bit. Therefore, the exact length of the second set of colors, each color would be ceiling of log n plus 1 bits. But then this is nothing but ceiling of log n plus 1 bit positions. That is because for every real number, ceiling of x is the same as ceiling of log x. So, you can prove this as an exercise. I am not going to prove it here, but I will be using it here. Using this equality, we write L2 as ceiling of log n plus 1. And if n is sufficiently large, I can say this is less than or equal to 2 times ceiling of double log n. So, we find that L2 is at most twice double log n. These are the colors that we have after the first iteration or at the beginning of the second iteration. Now, in the second iteration, continuing in the same fashion, we find that L3 is at most ceiling of log of ceiling of 2 log of log n. The ceiling is not needed, which is equal to ceiling of log log n, which is triple log n plus 2, which you can write as at most twice triple log n if n is sufficiently large. So, for a large enough n, you can write L3 in this fashion. So, continuing like this, we find that Lk is less than or equal to twice log k of n, that is logarithm applied k times on n, provided that n is sufficiently large. If n is not large enough for the algorithm to proceed for k iterations, so much the better, the algorithm would terminate earlier. So, in the worst case, n is very large and the algorithm proceeds for k steps. In that case, the colors that we use will have a length of at most this much. Now, let us say we continue the algorithm for log star n iterations. So, if k equals log star n, we find that Lk is less than or equal to twice log k n, but log k n by the definition of log star n is less than or equal to 2, therefore, this is less than or equal to 4. So, if you continue the algorithm for log star n iterations, the length of the colors would reduce to 4. If you repeat the algorithm for one more step, we would be forming 3-bit colors. That is because now we have 4 colors. After log star n steps, we are left with 4 colors, 4-bit colors. So, the bit positions can be represented using 0, 1, 2 and 3. So, there are 4 bit positions to represent. These can be represented using binary representation 0, 0, 0, 1, 1, 0 and 1, 1. So, you require 2 bits to represent the position numbers and then you concatenate 1 bit in the end. So, you require a total of 3 bits to represent the new colors. So, if you repeat the iteration, we will be left with 3 colors, 3-bit colors. 3-bit colors mean 8 colors. So, now we have reduced the initial n coloring of the linked list to an 8 coloring of the list. So, to recap, we run the algorithm for log star n iterations. When we put k equal to log star n, we find that the length of the colors that are left would be at most 4. So, now we are left with 4-bit colors. 4-bit colors entail a 16 coloring. If we repeat the algorithm once, the number of bits would reduce by 1 again. So, we will be left with 3-bit colors. 3-bit colors entail 8 colors. Let us see what happens if we repeat the coloring once again. So, right now we have 3-bit colors. So, the bit positions are 0, 1 and 2. There are only 3 positions. The binary representations would be 0, 0, 0, 1 and 1, 0. Therefore, if we repeat once again, the log star n plus second iteration will cause us to have colors of this form: 0, 0 with 1 bit concatenated, 0 1 with 1 with 1 bit concatenated, 1 0 with 1 bit concatenated. So, we are again left with 3-bit colors, but then instead of 8 coloring, now we have a 6 coloring, because these 3 bits would represent only these combinations 0, 0, 0, 1 and 1, 0. Therefore, the 2 initial bits would be representing only these 3 combinations. So, in effect we have 6 colors. So, we have reduced from an n coloring to a 6 coloring. We have reduced the list from an n coloring to a 6 coloring in order of log star n steps. But then, as I mentioned before, log star n is at most 4 for all real values of n. Therefore, log star n plus 2 is at most 6. So, for all real values of n, this algorithm would execute at most 6 steps, and we would have come down to a 6 coloring. So, what we began with was an n coloring, and what we have now is a 6 coloring, but what we want is a 3 coloring. So, on an ER EWP RAM, we have managed to reduce an n coloring to a 6 coloring. Now, we need to go and convert this 6 coloring into a 3 coloring. Then we would be done. What we do is this. Let us consider the list. Let us say we have some coloring. So, we have a linked list that is 6 colored. We want to reduce this to a 3 colored. What we do is this: initially we make every vertex sleep. We will wake up only those vertices that have a color of 4. So, this vertex is woken up and this vertex is woken up. Every vertex that is of color 4 is now awake. These vertices will look to both sides. So, this vertex looks to either side. It finds that it has a 2 on one side and a 5 on the other side. It does not have a 1. So, what this vertex does is to adopt the least color which is not in its neighborhood. Every vertex that is woken up adopts the least color not in its neighborhood. But remember, we have woken up vertices of color 4, no 2 of them are adjacent. So, when they look around in the neighborhood, they are not conflicting with each other, because there aren't two color 4 vertices that are adjacent to each other. So, in this example, there are 2 color 4 vertices. When they look around, they find that color 1 is absent for both of them. So, they will adopt color 1 each. And next we wake up every vertex of color 5. So, in this example, there is only one vertex of color 5 that is woken up. When that vertex looks around, it finds that it has only one color in the neighborhood, which is 1, and it will adopt the least color not in its neighborhood. What I mean is that the least valid color. We are considering only colors in the range 1, 2, 3. These are the colors that we finally want. So, the vertices are looking for the least color least valid color not in the neighborhood. So, vertex 5 finds that it has 1 in the neighborhood and the least color not in the neighborhood is 2. Therefore, this will be recolored as 2. Now, we come to vertices of color 6. So, when I wake up vertex of color 6 and it looks around, it finds that it has both the colors 1 and 2 in its neighborhood. Therefore, the least color which is not in its neighborhood is 3. It ends up adopting the third color. There will always be a third color because what we are considering is a linked list. Therefore, every vertex has a neighborhood of size 2. So, there can be at most 2 colors in the neighborhood. Therefore, there will always be a third valid color not in the neighborhood. So, every vertex has a color to adopt. So, we are waking up the vertices so that no two awake vertices are adjacent to each other. So, in a sense, the awake vertices will form an independent set, and then they can all adopt a new color without conflicting with each other because no two of them are adjacent. And there will always be one free color for them to adopt because every neighborhood has a size of at most 2. The size could be 1 also. When we considered this vertex of color 5, it had only one neighbor. So, the size of the neighborhood is at most 2. Therefore, certainly there is one free color. As in the case of this vertex of color 6, it has 2 neighbors of colors 1 and 2 each. So, color 3 is free. So, that is what this vertex adopts. So, we find that after doing all this, the list is now 3 colored. So, we have taken 3 additional steps. We assume that every vertex has a processor. With this assumption, we can wake up any vertex that we want. So, we wake up every vertex of color 4 simultaneously. All of them will act simultaneously. They will scan the neighborhood. The neighborhood has a size of at most 2, and then it will find the least color not in the neighborhood and adopt that color. So, this will take only order 1 time for each color. So, we consider the 3 colors 4, 5 and 6. So, a total of order 1 time is necessary to reduce the 6 coloring to a 3 coloring. To summarize, what we have got is that in order of log star n time, a linked list of n vertices is 3 colored on an ER EWP RAM. That is it from this lecture. Hope to see you in the next lecture. Thank you.